sense.
Yeah. So maybe just before we start, there's a couple things. So I did old-fashioned printout of some assignments, maybe not really assignments, but just questions to get you thinking and maybe thinking about this lecture. So I'll leave these up in the front. There's one for the third lecture as well. You can take, if you even think about it on the plane back to wherever you're going as well. Grading or anything. Also, in the interest of time, since I know we have to be out of here tonight, I'm going to try to just go over half of this talk, and I'll try to put the rest of it in the talk tomorrow morning. So I'm going to skip the kind of the part where I talk about how we try to overcome Doppler shifts in this type of sensor, and I'm going to just talk about vapor cells here. Okay, so maybe just to remind you, what we're doing here is, you know, we have light that sets atoms up so that they're very sensitive to radio frequency fields that are incident on this sensor. So this is a container for atoms, a vapor cell. And the part that I'm going to talk about this morning is the effect of the vapor cell. So one of the interesting things about this, the way this works, if you remember, so absorption, coupling laser, EIT, and then application of microwave field. We split the line here, and then this is a measure of the amplitude of that RF field. One of the interesting things here that I always have problems talking with electrical engineers about is that they always want to talk about power, and that's because they're used to talking about antennas where you induce some oscillation of the electrons, and then you're reading it out across a resistive load, essentially. So there's actually a power dissipation, and that's where the emphasis on power comes from. Ideally, in this situation here, if there was no decay and the system was perfect, then the atoms are just completely non-perturbative. This is a coherent process, and you don't dissipate energy. The photons in the RF don't get scattered off in a different direction. They kind of are in the presence of the atoms, they perturb the spectra, and that's what matters. But what does disturb that electromagnetic field that we're trying to measure is actually the vapor cell. It can actually scatter electromagnetic waves. And so that's what I'm going to talk about today. And I'll show you an example of that. This is the stuff we'll see tomorrow morning. Skipping a lot. Let me see. This is the slide that I wanted to show you to motivate this. So these are the spectra of the EIT splitting in an RF field at different frequencies. So this one is at 10.7 gigahertz. This one's at 109 gigahertz. So there's quite a big wavelength difference between those two measurements. And these are both done in a conventional vapor cell, because this is still an experiment that I'm going to talk to you about tomorrow. But nominally, which is demonstrated by the 10.7 gigahertz data, is that we would get a linear splitting of the RF field as a function of kind of the applied, you know, we think it's the applied field here. And so that's true for this particular case here at 10.7, but if you look at the equivalent data for the 109 gigahertz, you see that there's a deviation here when we get to higher field. And that's because the vapor cell is actually reflecting part of the signal that's coming in here and creating standing waves and perturbations inside the vapor cell. And if you remember back to my first talk, one of the motivations for this is from metrology. And of course, this is something that's not good for metrology, right? You don't want the sensor to disturb the field. Okay, so we've worked very hard to make it so that this doesn't happen for many sensors that we would build. And I'm going to tell you basically the considerations that you have to make when you're actually trying to construct vapor cells for this application. And so there's a whole science of this. This is kind of one motivation for metrology. also increasing sensitivity for other applications like communications and radar is another motivation for actually focusing on the vapor cell and trying to engineer it for that particular application, not universally in all applications. And so here's a kind of a picture of different types of vapor cells that we use. So here's one of the MEMS fiber couple lasers. I showed you some measurements that were based on these, and I also showed you some measurements, although I didn't describe it, based on this type of vapor cell. These are kind of similar. This one's actually superior to that one, and I'm going to explain that in a second. There's a lot of science that goes into these. We also use photonic crystal vapor cells. So this is an imaging cell. This is like what you would use as kind of a CCD kind of to, in the most basic kind of way, to sense an RF field. So what this vapor cell is made to do is to prevent reflections of the RF off the walls, so that you would get reflections back and forth here like standing waves. So what it does is it engineers a propagation band gap transfers to the surface of the cell, so that you can get a nice image that reproduces the field that's into the pod.
What's the length scale?
So the length scale here, these are roughly on millimeter poles, and so this is, I think this is like 20 or 30 millimeters.
That's resonant for a certain
yeah, it's built for a certain frequency. Yeah. The frequency of this can be quite large because the band gap can be fairly large. This one is actually, I'll talk about it in more detail. This one has a narrower frequency. This is actually built to do two different things, which is to couple in the RF into a slot waveguide here, which, because the index of refraction of this silicon slab is much different than air, we can actually concentrate the field into that gap, increasing the field where the atoms are. But there's also a photonic crystal engineered around here to slow the RF as it propagates along this waveguide, which also increases interaction. Okay. There's other kinds of vapor cells you might want to make. One's for imaging in arrays. This is kind of part of the DARPA program that we're participating in as a contractor for somebody. But also making three-dimensional structures for this is also important. And so one way that we've developed to do that is to stack layers of these different materials and build up a three-dimensional structure in that manner. And there's a lot of, I'm not going to talk about much of the material science because this is not a really material science audience, but there's a lot of material science that goes into the selection of materials. For example, this is flow type silicon, so there's not a lot of absorption. Here, we use a lot of glass. The bonding is also something we focused a lot on. There's just one example of it here. To do the stack bonding is non-trivial. And also the machining of these vapor cells at scales, but not just machining that would take like ages to do, but machining that can actually go and be manufactured and scale, basically. Okay, so these are all actually laser cut structures.
If you are looking at this slot waveguide, where you slow down the RF, the consequence would be a Purcell effect or the Ripple interaction.
It is, and all these kind of things have to be done at low density.
Yeah, so then we have to reduce the density of your gas.
Yes. But what you're really doing is you're increasing just the E field of the RF, and so it can increase the interaction, but it increases the RF field much stronger than that. At least that's what we've seen. I mean, we see some broadening in there. We don't understand all of it yet because there's a lot of pieces that come into here, like the. So this slot in this particular device is around 500 microns, and there's a 200 micron interaction region in the center there. And you know, we haven't seen like increased loss though in these. I'll show some data. It's not super pretty data, but it's some data. And I guess I think it's because it's not really, those states are not as resonant as what we would think. Okay, so for metrology, we don't want the vapor cell to scatter the RF field. We want essentially would like the RF field to pass through the vapor cell and make the vapor cell walls visible. That's kind of the approach. So the formalism for looking at this is really kind of small particle scattering. And it's really not that different than a lot of the scattering that we're discussing in the meeting. So you have an incident plane wave, and then when the plane wave passes through the vapor cell, it scatters a wave, which is represented in some spherical wave if this is kind of small, but you can make it so that the shape matters here. I'm not going to talk much about the actual shape because that will makes things a lot simpler for us. And then there's kind of this transmitted wave. And so this plane wave, you would represent the polarization of the electric field in this plane wave as a part that's parallel to the collision plane here and perpendicular to the collision plane. And then you would have a scattering matrix that represents the effect of the particle on the plane wave. And if you get these amplitudes, then you also know exactly what the particle does to the polarization of the field as it passes through the particle. The most important parameters here in this type of in this thinking of minimizing the scattering are really the size of the particle, the size of the vapor cell compared to the wavelength of the target radiation, and then also what essentially is the complex, which for us will be the real index, because we choose materials that don't absorb, the index of refraction of the vapor cell material. So I'm assuming that our sensor is going to be placed in air, so the closer that our index of refraction would be to air, the more invisible the vapor cell would be. And this is essentially the phase shift of the wave as it passes through the particle. So we would like this to be small, and we also, if this is small, then we'll get also better results. So this kind of gives three different regimes that are important in this consideration. The first is that the Rayleigh regime, which you probably know from your scattering theory in school, is that when the particle is very small, essentially, although we also have a criterion that, again, the phase shift across the particle is also supposed to be small. And so, in the Rayleigh regime, this is just dipole scattering. So then what happens is the vapor cell acts as a dipole, and it's pretty easy to understand how to do that. Unfortunately, this isn't the total solution to this problem because of the difficulty of making these very small vapor cells. This criterion is pretty stiff. It's not hard to reach this for a broadband vapor cell. If you remember, one of the things that we would like to do is take advantage of that broad bandwidth that the Rayleigh atom offers us. This is probably the more important regime that we try to reach, which is called the Rayleigh-Gans regime, where the index of refraction here is, I guess, designed to be close to the medium which that's placed in here, air. And then also this phase shift across the vapor cell is small. And so this is also interesting here. If we could get it so that the phase shift was small, and this didn't really, this really wasn't satisfied, this would also give us a good vapor cell because the wave doesn't pass through the cell. It didn't change that much. So the way to look at the Rayleigh regime to the Rayleigh-Gans regime is this regime, you can break the vapor cell up into small piecewise pieces that each have a dipole in them. So maybe this is a bad example of a vapor cell, but because I drew these as equally sized dipoles, but if these are the walls of the dipole and we had, of the vapor cell, sorry, and we had a wave coming in here, there could be a dipole induced on each of the walls, and we might be able to treat each of the walls as one piece of the vapor cell, and then we just add up the sum of those, and we would be able to determine what or how the incident wave was scattering on the walls. The more general regime is called the me-scattering regime, and that's just the regime where multipole scattering is taking place, where we not only have dipoles, but we have quadrupoles, et cetera, et cetera. And we don't really want to be in this regime because this is complicated, and this expansion generally is good for most most kind of finite objects. And if you kind of already have a dipole resonance, you're going to get dipole scattering, and then you're going to get quadrupole scattering, and so on. So you want to be in the regime where we kind of eliminate all of this, okay, or at least be somewhere where we don't have that at all. The way to kind of evaluate some of this traditionally is to look at the cross-section of the object, and you can break the overall cross-section into a scattering cross-section, an absorption cross-section, and usually we assume that that one's small here because we choose materials, again, as I said, that don't really absorb RF electromagnetic radiation. But we basically characterize how good the scatter is at avoiding kind of scattering a lot of radiation by comparing the cross-section to the geometric cross-section of the vapor cell. So, for example, since these two are equal, if we just ignore the absorption cross-section, what we want is to have this Q SC to be much less than 1. That's kind of the regime where the electromagnetic radiation isn't scattered very much by the vapor cell. And I'll show you that we can do this over a wide range. Sometimes this thing, this thing is called the radar scattering cross-section. It's the same thing that's used to characterize radar scattering by object. All right, so here's an example of what we would call the metrology cell. So this is the walls of that vapor cell that I showed you on the 2 pages before, I think it was, with the holes cut in the wall. And then this is just a similar vapor cell with solid walls. And so this is a finite element calculation. And there's 2 things that this cell is better about. There's a plane wave kind of incident from the top here on both of these vapor cells. You can see that inside this one, there's a lot of structure to the field. It's not uniform at all, which is bad for a metrology measurement. Here, the field inside is uniform. This partially has to do with how these holes are cut from their shape. But also, this vapor cell, because it's essentially like a artificial material, because what we've done is cut holes that are much smaller than the wavelength of the RF field into them. We can do an approximation, which is a good approximation, that the index of refraction of the walls here is kind of the average of the air that's in the holes and the walls, which are silicon. So you can, by cutting holes in the walls, reduce the dielectric constant or index of refraction of the vapor cell to better match its environment, and that helps with reducing the scattering. The uniformity here is shown kind of in this plot. So if we would imagine probing the electric field with laser beams down the center of these 2 vapor cells, and these calculations are done at 80 gigahertz, so the wavelength is kind of similar to the size of the vapor cells here. If we were to pass through there, we would get a distribution of electric fields. The plane wave in here is normalized to 1, so if we were measuring what was outside the cell, we would get 1. Inside the cell, you can see that this distribution is shifted away from 1, and that's because of that non-uniformity inside of the vapor cell. In here, since this one has been engineered to try to make it more uniform, you can see that the distribution of fields that we measured through the sensing region of the vapor cell is more peaked at 1 by, you know, over it's over 10 times better than this one. I think it's more like 30 or 40. I don't remember the exact number off the top of my head right now. This actually shows the radar cross section for both of those. Yeah. Yeah.
Descriptions you have. You said holes, hotspots for holes.
Oh, so these like here. Well, I guess what? Oh, yes. So the holes here are kind of, in some sense, like preventing a lot of reflections in here. So this gives you a bit of interference inside. Oh, where the holes are. Oh, so maybe actually this cell is exactly the same as this one, and so these black parts in here you can see are the holes that are cut. And so there's 2 reasons to cut it this way. One is to make sure that field is uniform inside as much as we can make it. But the other is, you know, you do need structural stability of the vapor cell. So I will say that if we had no holes here, the structural stability is almost the same as with this cell, you know, here. So it's not like this one was much more fragile than the other one, the other consideration. It's more of a material science consideration. So what I've done here is I plot the radar cross section of the perforated cell and the non-perforated cell. So this is one with solid walls and this one is without. And what you can see here is for this vapor cell, the cross section was about 0.9 millimeters squared. So it's somewhere around here. And you can see that both cells perform fairly well, you know, maybe up to about 55 gigahertz. But the one that has the engineered walls is much better over a broader bandwidth. This is actually that first dipolar resonance that I told you about for the small cell with the solid walls. And you can kind of see that you know, it does go quite a bit above the geometric cross section. So up in here, it's really scattering a lot of radiation, and you know, this is probably a vapor cell you wouldn't want to be doing metrology with at these higher frequencies. And this just shows some other technical things about filling the cells. It's quite challenging to actually make these cells and make them so that we don't have charges that build up on the walls. So again, that's some material science, but you know, we're able to cut the walls to within about 15 microns of accuracy, and we usually can get the surface roughness down to several microns in a kind of a straightforward manner by treating them with some chemicals. So also we need to fit fiber onto these cells to fiber couple them, and that's a little bit challenging. There is science that goes in there as well, because there's several different kind of pieces of fiber that couple light in, because we transport very different colors of light to the vapor cell, and in order not to get too much attenuation, we have to splice the fiber near to the cell so that the fiber where we have a compromise in attenuation is not long. All right. So I have about 10 minutes or so left. So what I'll do is now talk about this other device, which is this photonic crystal receiver. And what the idea here is to try to get higher sensitivity by, call it like amplifying the electromagnetic field that we're trying to measure. So to try to get a higher field within the gap here. This is an early prototype device where I can show you essentially, this is more or less a mock-up, the key features. So there's a input coupler here that tries to impedance match free space to this waveguide. Then there's a slot in here. And then there's this photonic crystal where the light gets slowed down. And we get an increase by the square root of the group velocity and the electric field amplitude in here from the slowing. And then we get the normal slot increase here too, where this depends on the difference in the index of refraction of silicon, which is quite high at these frequencies, and the air. And so you get a good increase there. So most of our initial designs are designed to increase the electric field amplitude by somewhere around a couple hundred. Okay, it's important that in this slow light structure, that this is what people refer to as structural slow light, not an atomic or material slow light system. Because in the material slow light system, most of the energy is stored in the polarization of the material, whereas here, most of the energy is stored in the electromagnetic component of that polariton, and that means that you do get an increase in the electric field amplitude in here. Okay, I guess that's that slide. One of the fun things about this is you start to learn about new things like band structure of the photonic crystal devices. This is just an example of that. I won't spend too much time on it as we're kind of running out of time, but we can actually start to, in some of the next slides you'll see here, to engineer these band gaps here. You see some evidence of white lines for this. And in here, these are some of the special points that Valentin talked about last night with respect to excitons. These are just this is the reciprocal Coulomb lattice, and it just corresponds to different directions in the crystal. And we mostly care about this K point here. This is just an example of a hexagonal crystal. There's nothing special really about it. That's what we're using for this device. So the other nice thing about this, like I said, is you can engineer these devices. You have good parameters to do that. You can move different guided wave bands through this band gap if you want to engineer this. And this just shows, gap guided mode in one of these structures over here versus an index guided mode over here. This shows that you can actually change where that band gap is by changing the structure. So this is actually just manipulating the gap here, so changing the gap. So we do things like this to impedance match the RF into and out of the device, as well as do other things like make reflectors and such. In the building of this device, here's another prototype. It's a fiber coupled actually. And it also shows the group index increase as you go towards the band cap. So this is just kind of like any other waveguide where you get an increase in the group index of refraction at the band edge. But what's shown here are some simulations of different wall angles that you can manipulate. And these angles are shown because these are kind of what we can do with the laser machining. So we can change the wall angle, and we can kind of even concentrate the field more into the localized region in that structure. So here is actually a 2-port device that we started to use to measure band edge. So this is done in a RF setup with a network analyzer. And as you tune the frequency, and you would stick this end of the device, sorry, you can't see very well in here, into a waveguide, and then this into a waveguide. You can measure the scattering parameters, the S parameters for the device, and you can locate where the band edge is for this, and that's what these are for two different devices. So again, you have to have a lot of when I do some of this stuff, you have to start to develop skills in areas that you wouldn't normally have thought you were you were going to do. This is actually a real device. This is one of our first devices. We've just started to work with these and actually get data. I'm quite proud of this device because even the bonding to get this together is kind of was challenging to do, but I think we've got that under control. Uniform, you know, we kind of make lots of devices now, almost none of them fail, but the bonding is almost perfect. So there's a lot of, there's no bubbles or sodium pooling or anything with this device. So that took a bit of work to get going well because, as I said, there's a lot of technical challenges in this you have to pay attention to. So for example, cutting these holes and then bonding on top of them is also kind of non-trivial. Also, I've also said a lot of times about getting narrow line widths in these structures because it's different than magnetometry or clock because the Rydberg atoms are so fragile. So in this device here, this is an EIT line that's I think it's around 15 megahertz, and this one is a D state. You can see a little broadening here from electric fields on the wall in the D state, but this is an S state, so it's more symmetric. But still, 15 megahertz here and about the same here. And these are also filled with a getter. You can see that, again, the projector is not the greatest, but you can see a little pocket here where that's what the cesium is located. Okay, yeah, maybe, yeah, those are much better. I can see it from here. And then there's mirrors here to guide the light down this channel and then out to probe. So this is some of the first data that we had on these devices. So the frequency chosen was around 35 gigahertz. And the only reason we chose this is because of the tooling we had at the laboratory. These are built on 4-inch wafers, and they're also kind of a millimeter thick. That's the design, so that they're fairly strong, and those are kind of silicon wafers that we can get. So this shows various kind of test cases. This is for the open waveguide. This is actually coupling the device to the waveguide, and you can see that there's an absorption here that's around 34.75 gigahertz right there. So if we go to measure that, here's an example. One of the tricks of this, which is difficult, is to overlap the device resonance with the Rydberg resonance, okay? And we tune this device by placing a very thin slab of glass next to it, tuning it. But this data that I had to show you is not where we've tuned the device, but where we've gone off resonance with the microwave or the RF frequency and shown a measurement here. So the green curve here is really with no radio frequency incident on the device. The blue curve here is if we go in with the wrong polarization. So the input coupler and the slot need a particular polarization to actually couple into the device, because it's polarization sensitive. And then this is if we rotate the antenna to put the correct polarization into the device. And it's offset because the microwave is tuned off of the Rydberg resonance. But if you look at the data here, the splitting, and there's an asymmetry here, so there's still something else happening. The enhancement factor is about a factor of 100. It's a bit below our target, but this is, again, some of our first devices, so there's a lot of improvements that we made and a lot of understanding of exactly what's happening in the spectra. I will say that part of the perturbation of the spectra is because in this device, we chose to just cap it with a slab or a thin sheet of silicon, and there is a reflection that comes off of that. This is just a thing to make it easier for us to produce more of these devices and test them, and vary the structure of the device so that we can kind of get more results faster. Okay, so more to come later. It's not perfect, but at least like the 0th order at work. And think what it really demonstrates, along with the metrology cell, is that you really want to choose the engineering of these vapor cells, even choose the engineering of the overall system to meet a particular interest. So this is probably not a great device for metrology because it depends on the structure of the vapor cell a lot. And but it is probably a good device as a receiver for something like radar or communications, because it does amplify the electromagnetic field quite a bit, and it makes this device, particularly competitive with really good standard receivers, which have noise factors of around 2.5 dB, and this device has a noise factor of around 1.8. So that's a pretty good improvement for this. And also, I should say, this is an all dielectric device. That's the other important thing. There's no metal in this device at all. So, one of the problems sometimes with antennas and receivers is that you can't put them next to each other, so they start to interfere and talk to each other. And this one is less susceptible to that. And I'll also say that noise figure is calculated without anything like a dish or anything like that, which most antennas for those kind of applications would have. With a dish, you can collect more RF and then couple it into your receiver. So this is really just the back end, and there's no amplifiers or anything. That's just the raw sensitivity of it's a reflection of the raw sensitivity of the Rydberg atoms in this structure. And then the other example, the metrology cell, right? That one we don't too much care about making the sensitivity so much higher to detect small signals. What we care about is that the vapor cell doesn't perturb the RF field. So the structure of those two devices is extremely different, and the ideas that go into their construction is different. All right, so with that, I guess I think we're running out of time. So I'll end here, and I will do the other lecture. You won't miss out on anything on tomorrow morning. I'll try to fit it in. All right, thanks.
I do some of this, there's structure analysis of your vapor cell, like oftentimes, like some optimization for get the structure just right, and like some cost function. So wondering what was the sort of structure of the parameters
For which the receiver or the other? So what we really cared about was to try to get a uniform field inside first, and then that was kind of varying the whole parameters and looking at that with electromagnetic simulators like LEAP and HFSS, and then secondarily to then choose the hole to I guess the filling ratio or something, like say, to try to match the dielectric constant. So there's also kind of a materials issue too, which we kind of constrained ourselves to in this design, which was that we were going to make the frame out of silicon because of the bonding that we use. We've recently developed, which I can't kind of talk too much about, similar low temperature bonding schemes for glass on glass, and those will be better because then we'll be able to better match the index refraction, and those cells will be even better than the one that I showed there. I think I answered that. Yeah, so uniform in field. Like,
yeah, I was just wondering, a couple slides back, you showed the spectrum for 49S, and it looked like the background had emitted like an oscillatory at one more slide. Yeah, it looks like there's some kind of oscillatory.
oh, this one right here.
Yeah, I'm wondering if you know what that could be.
This is just because we were trying to turned the lasers way down in this particular receiver that we measured in to try to get the narrowest line width, and To be honest, I don't quite yet know if this is like the limitation, so that this is broadened by background gas. There's still some inhomogeneous fields in there that are broadening out to 15, so we're trying to get out to lower Rabi frequencies to get the narrowest one. And so you're really just kind of seeing maybe not such a great measurement. Doesn't all look exactly great.
So I think earlier on you mentioned that when you're filling these vapor cells, like you guys have to do a lot of work to like get rid of the surface charges.
Yeah.
I was wondering if you could like discuss this in a bit of detail. I feel like other quantum sensors kind of suffer from this.
I can't really talk about that.
Okay.
Yeah. That's one thing you can talk about. Sorry, that's part of being a company.
In the first part where you have to sell and engineer the proposition, so you make the field from B. How big is it like? Is it just millimeters in the middle?
This one we assumed was like a 200 micron spot in the center. 2 to 400 we into the page. Yeah. So the plane wave is incident from the top. So it's as if this cell was sensing and the source was back there, and then the fiber coupling would be, to the top where the windows are. I'm only showing you one angle here. You really should do you have to do like calculation and for all the different orientations.
The fiber holder stuff, you have to worry about how to or that's small.
You have to worry about it. So when you get up to the higher frequencies, then that starts to matter, but it's not so much of a big deal. Where this going wrong. Yeah, so this cell we'd probably be confident with the fibers using it like in this range. When you can already start to see the dipolar resonance coming up here, and then with the glass on it, some of the stuff will be moved down with this cross section. But our initial measurements don't really indicate that it's like destroying the whole range. So we actually stick these things in an anechoic chamber and then measure against the horn. Then also we look at the correlations between the cells too. So to measure to stick them closer and farther apart to see when they start to essentially talk to each other. I kind of said they could come pick them up here.
The glass now, do you have to, what kind of special treatment can you do to it to eliminate the stray charge?
So for the glass cell, we're not really doing that. We're so in a traditional vapor cell, like this is made of blown glass that we use for tabletop experiments, we're not doing anything special except using a larger vapor cell, and the walls are kind of farther away from the measurement region. So when I'm talking about we're doing special things to the vapor cells, these small vapor cells, and then the photonic crystal vapor cell, those ones we can do things to the walls. The charge still may be an issue if in those bigger vapor cells, but it's not as big of an issue because it's just larger. The walls are further.
So yesterday I mentioned the glass has resonance.
Yeah.
Is that an issue?
So the size of the cells that Dylan's talking about are much smaller, right? These are kind of more like millimeter size scale, not micron size scales, and that makes a difference. That's a consideration, actually, design consideration for. I think Hossein kind of was getting at this for this vapor cell. So this is a 500 micron slot. We're using kind of 150 micron beams to try to go down the middle here of the slot so that we don't have to worry so much about what Tillman's talking about, that the walls will absorb the RF or the decay from the. I mean, that's also kind of one of the reasons why the really tiny cells that are stemless are very hard. I think we can make like, maybe 4 millimeter square, 1 millimeter, 1.5 millimeter thick vapor cells. We can do that pretty good, but getting smaller than that, it kind of starts to get pretty challenging.
So let us thank Shaffer Lecture. Thank you.
You looking for you?
So we seem to be doing, courtesy of course, Jim, doing reasonably okay on time. So what I suggest is that we take your 24 5